Look closely at the pristine exterior of a modern laptop or the edge of a high-end appliance. We perceive them as having sharp, crisp edges, but true sharp corners in sheet metal do not actually exist. Every crisp line you have ever run your thumb along is, in reality, a fold with a radius, and the size of that radius has absolutely nothing to do with a designer's aesthetic vision. The visual crispness of that edge is a strict mathematical output. It is arithmetic. That geometry is locked in the exact moment an engineer in another room finalizes two variables, the grade of the metal and its thickness. The person drawing the shape is handed a minimum limit based on those materials, turning what looks like a creative choice into a rigid engineering boundary. To see why that limit exists, we have to look past the finished product and zoom in on the physical reality of the sheet metal itself. This diagram shows a cross-section of a metal sheet bending downward. As the metal folds, the inner surface is forced to compress, while the outer surface is forced to stretch and elongate. The tighter you make that corner, the more that outside edge has to stretch. If the fold demands an elongation beyond what the material can handle, the outer fiber simply cracks. Before a crack happens, manufacturers check a specific measurement, the ratio of the bend radius to the sheet thickness. The industry calls this the R/T ratio. It calculates the exact elongation a curve demands against what the metal can actually give. The math dictates exactly how tight you are allowed to make the fold. The physical tolerance of the metal entirely strips away the designer's visual preference. Here is where the math creates a trap. As a material's physical strength rises, its total ability to elongate safely falls. If you specify a stronger material so a part can survive a heavy load case, you decrease its capacity to stretch. That means the minimum allowable bend radius must increase. The corner gets visibly softer. You end up with two teams pulling on the exact same variable in opposite directions. The engineers demand higher strength for function, while the designers want a smaller R/T ratio for crispness. You can have the strength, or you can have the crispness. And the manufacturing process itself hides a physical trap. This diagram shows a standard mechanical punch tool pressing into a sheet of metal. When using high-strength grades, the sheet physically lifts away from the punch tool during the bend. Because of that liftoff, the actual radius the material experiences is significantly tighter and more dangerous than the smooth curve of the tool pressing it. Standard metrics measure the tool, not the part, deceiving the designer. Every request for more physical strength carries an invisible bill. It compromises the crispness of the final design, and it shrinks the actual safety margins on the factory floor. When you pull back and look at the broader consumer market, you see these immutable physics dictating the final forms of entirely separate competing products. Structural thickness is chosen to ensure stiffness. Material grade is chosen to handle crash performance. Both decisions are locked in long before anyone sits down to detail a corner. Because competing brands in the same category often rely on similar stock materials and thicknesses, they inherit the exact same structural math. That is why so many different products share a microscopic family resemblance in their details that nobody actually designed. The minimum radius is handed to the designer as an absolute fact. Every fold on the object, the return on a panel edge, the corner of a chassis, is blanketed by that inherited number. All of these variables collide in one specific window of time, the concept phase. This is the singular moment where the physical fate of the object is permanently locked in. The concept phase is exactly where we work at Depix, because design decisions are as cheap as a sketch early on, but they become brutal once they are tooled. You have to see every angle and understand every constraint before you build.